Thank you. So I'm Thomas, and the ones who have known me and have listened to me last time know that I'm really keen on understanding the phage proteins, which are synthetic, the dark matter. Why are there so many proteins? I have no idea. We can't compare to anything. And we're using machine learning, using graph theory, and today we'll talk about using protein structures. So the reason is, if you look at here, genomes and their mutations, then more than 80% of the proteins we can kind of recognize, can assign some kind of function or similarity. With phages, vice versa, it's 2/3 of them we cannot identify. There are no hits in the databases. We cannot infer any function, and it's quite normal that we sequence a new phage and can't recognize any of the proteins. The genes are in front of us, teasing, but we cannot find any function. This is because they're so diverse. If you look at proteins from 10,000 genomes and compare everything against everything, you can see in the heat map that there's a lot of similarity between them. If you go into the phage space, it looks much more preserved. So there are already phages which are closely related, actually the proteins match each other in sequence space. So this is the reason why we tried, okay, can we actually move from sequence space to structure space? So proteins in the sequence, but actually in cell, they get folded into protein structure which then form a logical function. Maybe you heard, we've been today several times about AlphaFolds. So go from a protein sequence to a structure is hard. It's really hard. This hasn't been really solved. It's really hard to actually get to a correct or a decent protein structure. Until 2 years ago, when AlphaFold came out, and really revolutionized, because suddenly you get scalingly good prediction of the structure. It's published in Nature. It's not my publication, unfortunately. It's love to be on the one. But AlphaFold is really good, but it's kind of slow. So now servers, it took us predicted structure to predict 30,000 phage proteins over the last 2 years. But we wanted to predict all complete phage protein universe. A couple of weeks ago, a paper from ESM-Fold came out. The program ESM-Fold has been already around for more than a year or so. AlphaFold uses small sequence templates to deep learning to predict structures. ESM-Fold is using large language models. It's actually just an auto-completion. It's also very accurate, not as accurate as AlphaFold, but so we can use it for inferring functions. And it's fast, slightly faster than AlphaFold. So in our machine, we could predict 4.2 million phage proteins within 3 months. This is what we have been working with mostly. So what we are doing is we collected from antimicrobialresistance database, from our phage cloud database, 4.2 million phage proteins. We predicted structures with AlphaFolds and ESM-Folds, and then we created PyAlpha database so that the different proteins we run also the Brox annotation on all the proteins, that we can categorize, can cluster and group the different cluster of the structures into functional clusters, and then create this database. And then we started playing around with what can we do with it. So we can start with a protein which we know what it is. It's from Marcus lab. It's from a Salmonella jumbophage, DNA adenine methylase, and let's compare it to structures. How can we use the structures by analyzing it? So there are 3 different ways to do it. First is TML-Line. It's a program which can take 2 protein structures and align the structures in structure space. It's quite fast, a couple of hundred per second. But of course, we wanted to do everything against everything. We want to cluster the whole alpha database, 4 million structures against 4 million structures. That would have taken 15 years. So we didn't do that. There's another program called FoldSeq, which makes a quite clever side step. If you keep learning, to reassign the alphabet, and then it could cluster in structure space, in same structure space, and it took us just 3 days to cluster these 4 million proteins. That means then we could have clustered. If we have different clusters where we, for some of them, we know what the function is, then there's a lot of hypothetical proteins in this cluster, so they get dragged in, and they can then get assigned these functions. So that means we can also go back, create a new database, past database, and we can use Diamond Blast for assigning them. So TMR9 is the one where you do structure against structure. It's the most accurate, but it's also quite slow. So for one protein, it takes 3-4 hours. And then can randomize it. Baltic, quite fast, but we don't use it anymore because we've already created databases for Baltic. And then the Diamond Blast against the clustered database is the fastest. So then we also lose a lot of the specificity. So now on, we actually only use them the TMR9 part. So how does it function? So here we can back to this DNA metylase from its jumble phage. And here we see the full bacterial tree, phylogeny tree. When we just use normal blast against NR, we get hits to phages from Salmonella, E. coli, India, chicken. Oh, they're usually suspects for this. If we then just jump into structure space, we predict the structure, and then we get hits over the whole phylogeny tree. Most of the closest, of course, are from Salmonella, E. coli. Then the next group, which is the closest, are actually cyanobacteria. You can see this is the cyanobacteria metylase, right side, compared to Salmonella phage, phage, and compared to Salmonella phage. They're quite similar, very similar in structure space. There's no sequence between them all. And exactly why there's a strong connection between Salmonella phage, this jumble phage, and cyanobacteria. I had discussions with Andy Miller and Martha Cloak about it, and any questions I direct to Martha because she was working on it. Okay, can we actually use this structural information to have a better functional adaptation of phage proteins? Let's try it out. Again, working with Martha's phages. This time is the CD phages. We have a collection of them, and for several we don't really get a lot of good annotation. So here we pull out the hypothetical protein. We've tried everything. We blasted it. We machine learning it. It's still, we cannot get any idea what it is. Let's jump into structure space. Some people who maybe work with structure can already recognize it just on structure what it is. We compare it with our phage structure annotation tool, and we find very, very similar structure, and it is already a known major capsid protein. If you can read sequences, you can see they're not similar. If you're doing alignment, you can see they're very, very similar. So you would never pick that up in your blast or anything else. But with that, we could go back to Martha's CD phages, and you can see we see these phages. 3 of them had annotated major capsid proteins, 3 of them didn't find it. Now we have the structure space, we can actually starting assignment. Okay, can we use that in the can jump again back to the jumble phage. There's 257 proteins. You can see the original annotation several years ago. Only 13 proteins had a functional annotation. If you run procs, the procs in market models, which are weight tool, one of them, you can see we get a little bit better. We get 70 proteins allocated. If you jump into structure space, can you do a little better? You can. This jump phage, so we can jump from 13 or 70 up to 213 proteins annotated. And this part, if you can annotate it, if you can just easily transfer information from one structure to another, this is the part we still need to work on. Where are the thresholds? It's not like cloud, you can just use a hits threshold. This is so this is maybe a little bit on the positive side, but this at least we can the full functional annotation, you can get a hint if you really want to know where the structure protein is, where the line is, where other proteins you can't find it quickly, you maybe can get a hint from here. This is a tool now which we, in lack of imagination, called FASTA, phage structure-based annotation. It's not ready yet. Hopefully, it will be out of it in December this year. And if then we will find it on our website, Phage Compass, which is University of Copenhagen and University of Leicester, where we have our machine learning tools and hopefully the structural annotation tool later. So first, just to use it for transferring information. Can also get to learn something with evolution. Can we learn anything about how we know how it looks in sequence space? Very interesting. How does it look in structure space? So we have 4 million phage protein structures. We can do this clustering. Here, what you can see here is clustering of just 8,000 of this protein. That was 2 pens. Every circle you can see is a phage protein. The color of the circle is colored by the annotation. The size of the protein is proportional to the size of the size of the circle, proportional to the size of the protein. And you can see the circles have some borders, and these are by morphology, so blue borders are SIFO, green borders Podo, and red Mayo. You can already see that it's not separated into the different morphologies. What is interesting to see here is if you zoom in on this big blob here, when you have edges between the different proteins, that means that they are connected. If the edge is cyan or light here, then there's sequence similarity between the proteins. If it's a red edge, there's no sequence similarity, but only structure similarity. You can already see here this big cluster, which happen to be the major capsid protein. They are not connected in sequence space, but in structure space they are very connected, which is not a big surprise. People working with the compound fold. But we can also see other big blobs. So here we have all some of the integrases. Here we have some structure, the portal proteins, but we have another different cluster portal proteins, then we have another cluster portal proteins. So some of the proteins will cluster into one big cluster in structure space. Some of them in several different ones. So how does it look? Why is that happening? Is there any logic behind it? So we started looking at, so for example, if you then look at not only the 8,000 but the 4 million proteins and their clusters, we can see the portal protein. We have 320 different clusters in the sequence space. If you start into a structure space, they get reduced to 32 structure clusters. For the major capsid protein, if you can see here, is that we have almost 500 different sequence clusters, and they get reduced into 30 different structure clusters. And so DNA helixes, helicases, it's much more extreme from 150, actually just to review 3 structure clusters. So is there is the same different protein functions? So here we have a kind of a Nautilus graph of the all different protein functions in different phage space, and sorted by how reduced it gets from sequence cluster, from non-sequence cluster down to the structure clusters. I can't read it here, but for example, so up here are the ones which get reduced quite heavily. The best, the most extreme one is the iron oxygenase. We have 139 different sequence clusters, but transfer cluster in structure space is only one single fold. The structure only one cluster, but the sequence not more. And then we have others like helicases, endonucleases, and so on. Then we have another side, the other extremes, where there's no reduction. And by tradition, I really don't know hardly any of these proteins, like the lysines, lectins, and so. But you have the pentapeptide. There is only one big sequence cluster. It's not a small cluster, but the big entity can also just is also only one structure cluster. There's there's no difference. Same also sort of lectins, we have 19 different sequence clusters, and we can already get reduced down to 14, and more. So there's some biological function. So now we try to understand what it is, and we need to talk to some biochemists to understand how does it work in the function. And then we wanted also to understand the evolution of the different vectors, but the postdoc was supposed to do the analysis. It was sick, so I can't do that. I have to postpone that to next time. But I can finish now that in case some students are interested in learning more about it, we are running our computational phage course in November, which is these 5 intense days. It's me and Mother Cloaky and the winners. And we learn everything from phage annotation, both in sequence space and in structure space, and how to assembly, how to get from one phage sequence reads to schema which you can doesn't let CBI. And the students will work with the phages with its collections of the rainforests and students are left with doing. And acknowledgement, so this work is done with Marcus Andy and Gemma von Lund. And if you're interested more about tools, genome predictors, all the ones Martin already mentioned, also the CSR, you can look at online the phage clouds, and so then you're welcome to do it outside phage clouds. With that, thank you for your attention.